straight. So, things can travel in a line, or like a car going down a road, right? That's in a line, stuff like that. Another common one is like a parabola. That's a very common one, right? You throw something or toss something off right? If you throw something, it goes up and then it comes back down, very poorly drawn. Or like, even if you toss something off, like maybe you're on a building and you toss something off a building, right? You still get a parabola. It's just, kind of starts up here. Um, Almost anything that has free fall and gravity working on it is a parabola. So that's a huge one. And then another one that I thought of that we won't really, I don't think, get into, at least in this chapter, is I thought of circular motion, right? Like, I don't know, wheels on anything going around in a circular motion. Um, Circular motion is everywhere in life, right? We kind of um, forget how much it exists, but it is absolutely everywhere. So those are just a few that I thought of. Um, okay, so I I don't know if I would really worry about um, writing all this. You might want to sketch this little picture right here, and you might want to like label what each of these are. But objects that are launched, thrown, etc., in some way are called projectiles. The path of a projectile is called its trajectory, and the horizontal distance that a projectile travels is its range, which I think is a little weird because usually we say range and we're talking the y's, right? But in this case, the range is how far it is, traveled to throw it out or whatever. And so the following figure represents the initial trajectory of a football being kicked. It could be literally any object being thrown at whatever angle, right? But for our sake, we can make it a little more concrete, and we could say, hey, this is like a football being kicked, right? The magnitude of the initial velocity v, so this v should be a speed, and it has an angle with the horizontal, and this can be described by its component vectors, right? We can, with every vector, again, hopefully, one thing we came away with this project from that was kind of a goal of mine, vectors are just right triangles everywhere, right? If you break up a vector into its component parts, it is just right triangles, which, like, hopefully, with the right triangles, we are just, like, super comfortable with our trig and right triangles. That's, like meat and potatoes of this class is trig, which is mainly to deal with right triangles. So hopefully we've kind of realized that vectors are just right triangles, right? If I were to take this and tip to tail it, right, there we go. There is our right triangle. So maybe you could write it like that, right? We've taken this vector, this initial velocity at whatever angle we've kicked it at, and we've broken it into its x and y components. And maybe just to keep vocabulary up and maybe fill in gaps in case we missed it, this would be the magnitude of this vector, right? The length of this, or amount of force, whatever it may be. In this case, it's velocity or speed. That would be the numeric value here. That's the magnitude. And when I say magnitude and direction, right, here's the direction theta. That tells us how the ball is being kicked or whatever else. And then these would be your x and y components. And we can find these x and y components. All right, maybe. Okay, so if we want to find v sub x, right? If we had this theta and this magnitude here, or maybe I should write this first so we can see where it comes from. If I want adjacent and hypotenuse, I should do the cosine. Right, the cosine of theta equals v, or not v, sorry, v. Or I guess I didn't need to erase v sub x, right? Adjacent over hypotenuse, which is v, and so then we can get v sub x. Right, if I just multiply that v over equals cosine of theta times v. And a nicer way to write that might just be with the v on this side. So V times cosine of theta. And the book works with its magnitude. Remember, those little absolute value signs just mean magnitude. So we can work with it like that. And then the same thing for v sub y, right? If we took the sine of theta, we'd get opposite over hypotenuse, which is the v sub y over v. Multiply the v over to get v sub y equals v times the sine of theta. And we can just talk in terms of the initial vector's magnitude. So these two here, you might want to have written down. I'll give a second for that. So maybe like this diagram, either this way or in the right triangle way, and then write these down. I'll give it a little bit of time for that. And I'll actually go to the next slide because they're on the next slide as well, so don't freak out. The top, you don't have to worry about writing the top or this. I would just make sure, again, we get these down. I just wanted to show you where they come from, right? It's not out of thin air. It's just by doing, SOHCAHTOA on a right triangle. As the ball moves, so right, imagine we kick that football. As the ball moves, gravity will act on it in the vertical direction, and the horizontal component is unaffected. And a lot of times in physics, if anyone's taking AP Physics, I'm sure you've run into problems like this. For simplicity's sake, especially in entry-level classes, you assume that some things don't exist, like friction, or in this case, air resistance, right? So we're assuming the only thing acting on the ball is gravity. And so those two, x and y components that we came up with are parametric equations, right? Where this time we don't really have a variable t involved, but we've split it up into two separate equations, right? We have our x equals and our y equals, which is kind of like what we had before, except now it's a vector, right? A vector in the x direction and a vector in the y direction. And we can kind of see in this little diagram here how this ball looks when it's kicked, right? You kick it and it has a huge, vector upwards, but then as gravity acts on it, that upwards vector gets smaller and smaller until gravity is the one pulling down on it, right? Going straight downwards. And then you'll notice that the x vector is just to the right the same amount every single time because we're assuming no wind resistance. And if there's no wind resistance, then there is literally nothing slowing down the ball. So, and then this green one is the resultant of the two put together, right? And it makes this parabola shape. So for our first example, find the initial horizontal and vertical velocity of a stone, another typo, of a stone kicked with an initial velocity of 16 feet per second at an angle of 38 degrees with the ground. And hey, I'm telling you guys, vectors are just, you break them into their components and they are right triangles every time. And back when we said, or I tried to give like a little like overview. I was like, hey, what's one very useful thing to do with vectors in almost any situation or problem? And I said, component parts. Break them into their component parts. You get a right triangle. Right triangles, we love them. They're so nice, right? We can do so much with right triangles. So, we have this velocity at 16 feet per second, right? And at an angle of 38 degrees with the ground. Now, here's the thing is, right, you could have this written down and you could use these formulas, right? Or if you know that every vector just makes a triangle, right? And it wants the horizontal and vertical, right? Now you can just use SOHCAHTOA from here. But so that's just something like, right, like you don't have to memorize everything, right, if you just make sense of what it is, right? And vectors, when it comes down to it, vectors are just right triangles all over the place. But if we wanted to use these, right, so v sub x equals the magnitude times the cosine of theta, and we have our y component is the magnitude times the sine of theta, right? If you want to skip straight to there, we certainly can. So v sub x equals, our magnitude is 16 feet per second, and cosine of 38 degrees. And then I'm just going to do the y in the same breath, right? That's still 16 times the sine of 38 degrees. And my calculator is dead, so I'm just going to trust the book here. It says that v sub x is about, they got 13, and they got, and this would be in feet per second. It's a velocity, and they got that v sub y is about 10. Right. So